We'll now look at the convection theorem and try and just show its derivation, which will be used to construct the Navier-Stokes equations. First, we'll consider a volume, V0 at time 0, filled with fluid parcels, and another volume, V sub t, filled with parcels as they move in space and time. We'll write V sub t as y in 3 dimensions, and y goes as x at t for some x in V0. The volume element dy of particular vt, that's a volume as it's moving, is given by j at xt, the Jacobian, which is a transform of x going to x sub xt. This notation was denoted in our previous lecture. So we'll note that j is the determinant of partial xi of yj for 3 dimensions. And script or map script j will just be the determinant, not the absolute value of the determinant of partial x0 yj. So now we're going to be able to write a partial t of partial xi of yj. We can move the partial t inside. We'll say partial xi is uj now, which we can expand out with a summation of k equals 1 to 3, partial yk uj, partial xi yk. Then we can expand this out for k1, 2, 3 as 3 determinants of partial t, partial x y1, y2, and y3 across the diagonal. And the other terms are just partial x of y2, 3, etc. We can rewrite this using our previous definition at the bottom of the last page as a summation of k equals 1 to 3 for all 3 parts. Now we'll just, by definition, let at time 0, the Jacobian be unity. And then we can write the Jacobian at all higher times t for x go as e to the integral of 0 to t of the divergence of u along S. So this means that the divergence of u is a quantity that governs the deflation or shrinking or inflation or increasing above a particular volume with time. So this means that if we have, say, f, a time-dependent field over 3 dimensions, we might define capital F as that volume integral in time of the time-dependent field variable f, which is a function of space and time, y and t, dy. We can write that as an integral over the volume of little f with big xx t with the Jacobian we just defined. Now we can use the fact that partial t of f goes as the material derivative, which we showed in a previous lecture, and partial t of Jacobian goes as divergence of u of j, and j of x and t dx is dy, to find and combine these to find the convection theorem, equation 66, which we'll use to derive Navier-Stokes equations. So we'll have d dt of the volume at time t of our property in our field of f of y and t goes as the volume, the same volume, with the material derivative of f plus f times the divergence of u. We can also note that the material derivative of f divergence u goes as partial f partial t plus u dot nabla f plus f divergence u goes as partial t partial f of divergence fu, which is preferred form, in my opinion, for these equations. Using Green's formula, we can take the divergence of u in a volume and write it, of course, as a surface integral of that same velocity field u normal dotted with the normal unit vector on the surface. So after writing this for the surface element on the boundary of partial vt and vector v for the normal at partial t, partial v parting outward, we can write this equation, which we might also reference, as the time derivative change of that field variable f, function of space and time, will go as a volume integral of partial f partial t plus the surface integral of fu dot v over the surface of that volume. So this is like Reynolds transport theorem.